Hello, everybody, and welcome to my shell midpoint walkthrough for the CSC209 course. This is a technical walkthrough of my implementation of variable storage and expansion in my shell. I will demonstrate compilation, variable replacement, nested expansion, and finally walk through the storage and expansion design, including how tokens exceeding 128 characters are handled and specifically truncated. Also, please ignore this comments up here. We'll be using those for our demo. Let's begin by compiling our code. Go into the project, and then we'll go into the source file and clean up the previous compilation and compile once again. Perfect. Now we see that it compiled without any errors or with all the standard warning flags enabled, as you can see, so we can move on to variable replacement. Let's begin. We'll start by opening up our shell. And before I begin, I should tell you that we use a key value syntax just like Bash does. So if we execute course equals CSC311 and then say echo for that course, we'll see as expected, we get CSC311. Now, if we reassign that variable to CSC209, which is this course, and then run echo course, we'll see that we get CSC209, demonstrating a correct set variable replacement, which is perfect. What our set variable here is doing is it's traversing the linked list, and if the key already exists, it frees up the old value and replaces it using stirred up, which you'll be seeing shortly. It does this without creating any duplicate nodes, just changing the existing nodes. Now we'll move on to our storage walkthrough, and that is how our storage works. First, we'll start with the labeling with our linked list format. We have a data for each node containing a key value pair, which I talked about earlier. We also have each node of the linked list, which stores the data and a pointer to the next node, which is exactly what you'd expect from a linked list, making it intuitive. We also have free all variables, which we'll be getting into later, that is in charge of cleaning up all the memory during termination at the end of our shell usage. Now, let's get into variables.c, which is the actual bulk of our code. First, we deal with some edge casing for if the user tries to pass in an empty setting and return an error if so. Otherwise, we proceed to a while loop, where we first traverse the linked list to check if the variable already exists. If it does, we free the old variable using stirred up and return it immediately, which is what this does, assigning the value with this. If the variable does not exist yet, then we allocate a new node with malloc, we return it with stirred up, and we allocate a new node, we insert it at the head of the linked list with the following code, and we have an insertion of O1, which is very ideal and is a strong reason why we're using linked list. Now let's get into why we chose linked lists in general. The positives are it has a simple implementation. It dynamically grows as we add nodes, and there's no fixed size limit, so the user can add as many environment variables as they want, as outlined in the course. The negatives of it is that it has a lookup of ON, which takes quite a while. And for the future, I could implement a hash map, which would have an O1 lookup time, which would be a lot stronger. The benefits of it is that we still have an O1 insertion, and given that the typical user doesn't use many variables, its simplicity trade-off is justified with its simplicity. All right, now let's get to the meat and potatoes. That is our expansion and 128 character limit logic. First, I'll be doing a demo to show you how it works. Let's go to our little shortcuts over here and create A equals this and B equals this. And then we'll execute the following. Perfect. This behaves exactly as we want. This token up here intentionally exceeds 128 characters once expanded. because realistically, it can only take this many characters before expansion. That's why we see this. Notice that the hello at the end of the string has been truncated. It's been removed. This demonstrates that our shell is enforcing the maximum token length constraint of 128 correctly. And now we'll get into how this works by walking through the code itself, which is within my shell, and it's likely, no, it is the largest piece of code, but it's fairly simple in what it's doing. All right. First, we create a buffer of fixed size max string length 1. So we have a length of 128 plus one character so we have room for the null terminator, and we have a counter of 0, which tracks the number of characters. We see that here in the loop logic, where if we ever exceed the max number of characters, that being if we ever reach 128 characters total, then our for loop will terminate so we don't go over our limit. Now, the outer loop enforces it, and we also enforce it later on as sanity checks during our assignment of variables from our token. We use our variables to simplify the token logic, and this is the exact code responsible for the truncation within this for loop. When expansion reaches above 128 characters, the copying system completely stops and terminates, so our variables get cut off here. So our variable key gets capped off at 128 characters, and our variable value gets capped off at 128 characters, which is exactly what we'd want. Regarding the design of this, the positives of our expand token is that it prevents buffer overflow with many if statements and enforcements, and ensures memory safety with the if statement. With the if statement here, where before we give the user our new token, we check if we can allocate it properly. If we cannot, then we return null without allocating it, so that we don't have unnecessary memory allocated. We also run string compare buffer to token. So if our buffer is the exact same as our token, then we'll return null because we don't want to allocate unnecessary memory. We also have silent truncation, which is a slight negative, but it's realistic for the user to expect if they're working with Bash, as they should know about the 128 character limit. Memory is only allocated when expansion modifies the token, which is a better descriptor of this, and this prevents unnecessary heap allocation. Expanded tokens are later freed in the main loop at the bottom here, which we'll get into. This is the cleanup and the conclusion. So when we execute exit, what happens is our code runs free all variables, which traverses our linked list and releases all the allocated memory we've created within our environment variables. So we traverse each one and clean up and free each node, each data point, and each variable entirely. In summary, this implementation compiles without warnings, supports variable definition and redefinition, as well as nested expansion. We are able to handle an arbitrary number of variables, which is demonstrated here, and we enforce the safe 128 character limit, which we see at the cap here, by truncating the hello statement. Lastly, we clean up the allocated memory using our free all variable call and our free garbage collector. Because in past implementations we have this, which stores our tokens as variables, and then stores our tokens as variables and then frees them at the very end to ensure that we aren't leaving any loose ends in terms of memory. This design prioritizes safety, clarity, compliance, and compliance with project constraints. Thank you and have a nice day.